And now what we have here is our model with the objective function, which is this z here, which is the summation of all the variables that represent what we transport from plant P to customer C times the unit cost. So if we transport one truck from Haarlem to Amsterdam, that means X sub Haarlem Amsterdam instead of PC times 131. So if we do that product for every possible pair plant customer, which represents the shipping from that plant to that customer, and we sum all those terms, what we get is the total cost, which is formulated in this expression here in a compact manner. So that is the value we want to minimize, and it depends on something we cannot change, which is the parameter corresponding to the unit cost, and with something that we can and want to decide, which is the transport or the shipping of trucks from plant B to customer C for every plant and customer pair. But we cannot just pick whatever values we want from these values. We need to meet or to satisfy the constraints that happen in the real world, and we need to translate those into the constraints of our mathematical model. And we have two sets of constraints. One for all plants. So for every plant, we need to impose that whatever we're going to ship from that plant cannot exceed its capacity. So we have two terms in this constraint, and this symbol here, less or equal than. So to our right, the right-hand side of the constraint, which is actually the way we call it, RHS, right-hand side, is SP, which is the supply of our plant. And that is larger than this summation here, which is for every plant, if we sum this is the total amount we are shipping from that plant to all customers. So this is what we are sending from this plant, and it cannot be larger than its capacity. So this way, we are imposing the constraint referred to supply for every plant. And this second constraint here imposes the same thing but referred to customers in terms of their demand. So again, we have two terms, and we have this symbol here, which is larger than. So what we have to our right, the right-hand side of this constraint, is the demand of the customer corresponding to that constraint. And what we have to our left of this symbol is the summation of all the units we transport from every plant to this particular customer. So this is the amount that this customer receives from all the plants, and we impose that on every customer. So we make sure that all customers are receiving what they have demanded. Some might ask if this could be an equal sign. It could be as well, but we are allowing the possibility to the model to do something which won't do because it doesn't make sense, which is shipping more than what a customer has demanded. You can do that in real world. You can send more than what is demanded and just not getting money out of it, or not getting that actually received by the customer. So that is something that you can do, but the model won't try to do that because that would mean having a larger cost. So both larger than and equal will work. And finally, we will impose that all variables are non-negative. We don't transport anti-trucks or something, or we don't have variables which can be negative, meaning some reverse flow. No, it doesn't make sense. So we just have non-negative values. So either we don't ship any truck, or we ship a positive number of trucks from every plant to every customer. So this is the formulation of the whole model, where we want to minimize this expression here, subject to this expression that limits the values we can pick, or the solver will pick for us when solving this model, and always having non-negative values for our variables.